Welcome to this video on energy collisions, conservation laws, and conservation of momentum. Physics may seem complex, but at its core, it's all about explaining how and why things move and interact. These concepts aren't just theories, they are the foundation for everything from designing rockets to understanding car crashes. So let's dive in. Let's begin with the basics energy and momentum, which are known as the building blocks of motion. So, what is energy? Simply put, energy is the ability to do work. It can exist in various forms such as kinetic, potential, thermal, and chemical energy. An interesting fact about energy is that it can be neither be created nor be destroyed. It can be only transferred or converted. It is known as this sentence is known as the law of conservation of energy, which we will talk later. Let's talk about two types of energy, two examples of energy. That is, first of all, there is kinetic energy. This is the energy of motion. Imagine a speeding car or a falling object. The formula is Ke equals half mv square, where m is the mass and v is the velocity. Then there is potential energy. This is stored energy due to position. Picture a ball perched at the edge of a table. The energy is Pe equals mgh, where m is the mass, g is the gravity, and h is the height. Now momentum. Momentum is the quantity of motion an object has. It's calculated as P equals mv, where m is the mass and v is the velocity. Momentum is a vector quantity, so it has both magnitude and direction. Here's something fascinating. Momentum is what keeps planet in orbit and it helps us design safe vehicles. Now, let's talk about the conservation laws. The first conservation law is the conservation of linear momentum. It says that the total linear momentum of a system remains constant if no external force acts on it. The conservation of linear momentum applies to objects in straight line motion. The equation is momentum total or P total is m1v1 plus m2v2 equals m1v1 hash plus m2v2 hash. And for conservation of linear momentum, an example is if two ice skaters push off from each other, the combined momentum does not change. That's an example for conservation of linear momentum. Next is conservation of angular momentum. This applies to rotational momentum. It states that the total angular momentum of a system remains constant if no external torque acts on it. Like I said before, this principle is fundamental to understanding rotational motion and is frequently observed in systems like spinning wheels, figure skaters, and celestial bodies. For example, have you ever seen a figure skater spin faster by pulling in their arms? That's the angular momentum conservation in action. When the skater reduces their moment of inertia, the angular velocity increases to keep the total angular momentum constant, and we can see the equation here, that is I1 omega 1 equals I2 omega 2, where I is the moment of inertia and omega is the angular velocity. Next is the application of conservation of momentum. First of all, there is collision analysis. By applying conservation of momentum, we can predict the post-collision velocities. Second of all, there is rocket propulsion. which is rocket use momentum conservation to propel forward. When fuel is expelled backwards, it pushes the rocket forward. This is also Newton's third law in action. Here, expulsion of mass, that is fuel, leads to a change in momentum of the rocket. Its conservation of momentum is also used in astrophysics. Like I said before, momentum conservation plays a crucial role in celestial mechanics. It explains how celestial bodies interact, such as during gravitational encounters. Now, let's talk about some real life examples of conservation of momentum. First of all, there are car crashes, and that's the example of conservation of linear momentum. When two cars collide, the total momentum before and after the collision remains constant, assuming no external forces like friction acts on it. This is the key in accident reconstruction. Second, there is the conservation of angular momentum, and its example is a skater spins faster when pulling in their arms, the conserving angular momentum by increasing angular velocity as the moment of inertia decreases. Here are some images representing the conservation laws. Now let's talk about energy conservation. The law of conservation of energy states that energy in a closed system remains constant. That is, energy cannot be created or destroyed, only converted from one form to another. For instance, a pendulum swinging converts potential energy into kinetic energy and back again. And also here an example is given, that is when a ball is dropped, its potential energy is converted to kinetic energy. Also, like given in the picture, we can see a roller coaster, and it's a perfect example of energy conservation. At top, where the roller coaster is stationary, it has only potential energy, whereas when it moves, it converts into kinetic energy. Next, we are going to talk about other concept, that is collisions in physics. Collisions are fascinating because they demonstrate how energy and momentum work together. There are mainly three types of collisions. First, there is elastic collision. Second, inelastic collision. Third, perfectly inelastic collisions. First there is elastic collision. In an elastic collision, both momentum and kinetic energy are conserved. No energy is lost due to heat, sound, or deformation, making this the ideal type of collision in many theoretical and real life scenarios. For example, the, uh, the collision of billiard balls is an elastic collision, or two steel balls dropping into a hard surface where they bounce off each other without any loss of energy is also an example for elastic collision. The equations for elastic collisions are: final velocity of an object v1 is given as m1 minus m2 into v1I plus m2 plus 2m2 v2I, the whole divided by m1 plus m2, and the final velocity of second body is m2 minus m1 into v2I plus 2m1 v1I, the whole divided by m1 plus m2. And where m1 and m2 are the masses of two objects, and v1i and v1i and v2i are the initial velocity, whereas v1f and v2f are the final velocities. Now, the second type of collision, that is inelastic collision. In an inelastic collision, momentum is conserved but kinetic energy is not. Some of the kinetic energy is converted into heat or deformation. Though the objects do not stick together, the shape often changes and part of the energy is lost. And like I said before, a common example of an inelastic collision is a car crash or a bat hitting a baseball where the objects might deform but momentum is still conserved. And the colli- third type of collision is the perfectly inelastic collision. In this, the objects stick together after colliding, resulting in the maximum loss of kinetic energy. However, momentum is still conserved. These type of collisions occur when the object's shape change drastically and they move as a single unit after the collision. And an example is when two clayboards collide and form a single mass, or when two cars collide and stick together. Now, there are some applications for collisions as well. In particle physics, collisions help us study subatomic particles. And also in engineering, understanding energy dissipation during impacts is crucial for designing safer vehicles. We all have seen in like different ratings for cars, safety ratings, and that's done through this. That's a perfect example for collision in physics. Now, let's conclude this video by saying the laws of energy and momentum are the building blocks of physics. They explain natural phenomena from car motion to planetary objects. Did you know momentum conservation is even used to explain how galaxies form during massive cosmic collisions? Uh, Mastery of these concepts is crucial for anyone studying physics. Now, I want to end this video by quoting a famous words of the world-renowned scientist Albert Einstein. The laws of physics are the same for all people regardless of their race or nationality. The law of conservation of momentum is no exception, showing how universally applicable and beautiful the natural world is. Thank you for watching. I hope this helped you understand these incredible concepts. Stay curious and keep exploring physics. Thank you.